officially starting the recording. That means we're here together. Zoomers, can you hear and see everything okay? Waiting for the thumbs. There's some thumbs. Roomers can see and hear everything okay, I'm assuming. We're good to go. All right. So this is where we left off. Good news for me. In the middle of the age distribution as it relates to income in this example. More broadly construed, this type of shape, we would call that a quadratic trend. You probably learned parabola as a word for this earlier. How do we make this kind of shape in our data? If we expect to have a relationship that's bendy like this, what do we add to make that happen? I don't know the gestures. Yeah, square term. So if we add x, that creates a line. Adding x squared and x at the same time creates some kind of bendy pattern. So they both stay in the model. Other pictures of quadratic that I can show you are these. So it doesn't have to be a full U. It can just be part of the U. So this picture implies that if I kept going to the left, it would come back up. This picture implies that if I kept going to the right, it would come back down. So partial U's in all of these things. Do you want to see some numbers and then some code? Yeah, we want that. Okay. This is a different computer than I'm normally using, but it's hiding my PowerPoint thing. There we go. We got it. So in this example, I have age as a new predictor, but what does the minus 18 indicate here? Centered at 18. Why'd I pick 18? Any guesses? Say it again. Yeah, people who are eligible to make money, I guess, in terms of full-time work, or at least part of this survey. It's the lowest age in the sample. So I picked 18. So you will see examples of people centering towards the middle, but you can also think about it as minimum or maximum values. In particular, a minimum value lends itself nicely to the language, as age increases, right? Because you're starting from the lowest value that you have, and then that's as your reference point for the intercept, and then you can see what happens from there. But if we think about what the linear slope is for age, we also need to know where 0 is with respect to that, because that's the linear slope that we get back is at that point. So if I draw, to the best of my mousing ability here, a straight line over this point at 18, you can see the shape of that, the slope of that thing start to change like that. So there's an infinite number of possible linear slopes depending on where you are on this curve. The one that's going to come back out of the model is going to be the one where you're at 0 on that variable. So I've got age minus 18, and I've got age minus 18 squared. So then we know, based on the definition of an intercept, that the expected outcome value when your predictors are 0 is what beta 0 means. So in this context, this is expected income for an 18-year-old. Cool. That person makes no money. They make $2,600 in this survey. Linear age slope. So if I want to talk about the linear effect of age, that beta 1 only refers to that if this term drops out. So it is not just the linear slope of age, but it is specific to age 18. It is the slope at that point, because that would be where this term drops out. So that number ended up being 1.2, and it was significant. So we would say that for every additional year, as evaluated at 18, this side of the plot, income would be higher by about $1,200 per year of age. The quadratic then is half of the rate of acceleration or deceleration, and this describes what happens to the linear slope. It's negative, so that means it's starting out positive at 18 and becoming less positive and eventually becoming more negative as time goes on. And that is also significant. So we can use this information to make predictions at other ages, such as age 30. If I fill in 12 here, a 30-year-old is predicted to make $14,000 and some odd dollars. A 50-year-old is predicted to make $21,000. So at this point, we're still heading up in terms of the relationship between age and predicted income. A 70-year-old, though, is only predicted to make $13,000. So we're over the top. And there is a term that people sometimes like to compute, like the tip over point, I've heard it called sort of colloquially. Is there a term for this, Mike? Aperture is the one that I know of. You've heard that one? Yeah, so you can compute the age where the slope is at max income, where linear is 0. And so age 48.5 in particular is where the slope turns over. Yeah, exactly. Me too. So the plot on the left here, I made these in SAS. These are the individual data points, scatter plot. This is the predicted regression line from age and age squared. Do you see the blue shading around it getting a little bit wider as you go out? That's because there's less precision the further away from the mean you are on these variables. The dashed lines out here are meant to indicate the prediction interval, also taking into account the residual variance. So how much unknown information do we still need to try and explain? So that interval is a lot wider in terms of what we would expect. I plotted here the crazy lines. These are the means for each age, rounded into nearest 2 years. And I plotted predicted values through those as well. So this actually works, I think, pretty decently in terms of mapping this relationship. There's some noise out here that I might want to adjust for potentially, but this works okay. So for something like this, the slopes work together to describe the relationship between age and income in the same way that the slopes work together for our grouping variables of working class last time. So it takes both working together to make this trend. Therefore, we want to have a test of both. So the test of the model at this point, F, what's the 2 here for? Do you remember this? Which one? Numerator, yep. That means this one is denominator degrees of freedom. Do you remember where those terms come from? I'm getting there. This is where. Because when you build the F, it's what you know over what you don't. And so the what you know part is the numerator. We have information captured divided by the number of slopes it took to capture it. So it's like info per slope. That's the top. And then on the bottom is information remaining divided by number of slopes you could still add. Denominator degrees of freedom is the bottom. So then it's like, how well did you do per slope relative to what we would expect sort of from any slope, like as a chance almost level. So F, like theoretically 1 would be you did as well as expected by chance. In this particular number, this is 42, we did really well. So that's where those terms come from. Go back. Getting there. There we go. So 2 is the number of slopes in the model. 731 is the number we have room to add. F is 47. Is that good? I think so. R squared tells us the effect size that goes with this F. So we have accounted for 11.4% of the variance in income by these 2 slopes describing how age predicts income. So another way to think about this R squared, proportion of explained variance is the natural one, but it's also R squared. So if you think about how the model works with 2 slopes to make a correlation, it's through y hat. That's the key. So we create a new column in the data set. What is your predicted income based on your age? Okay, that's y hat. If I correlate that y hat column with the real y, then that's R. Remember how to square it? Yes, we do. We capitalize it too for good measure. So you can think of it as the correlation between y and y hat squared, or you can think of it as proportion explained variance. Either one works. What's MSE? What else might I call that? What's a synonym for MSE? I heard the word residual. It is the residual variance. The MSE is mean square error. Yep. Also mean square residual in some software packages, but it's residual variance. It's the variance of the E's across people, and E is what remains after being predicted by H. Yes, indeed. Okay. Do you want to see the code? We like code, don't we? If you do the code, you can finish your homework. So that would be even better. Come on. Where's my example? There we go. Why does this keep coming back? There we go. I want to start on, what page is this? 5? Yeah, the green box is like blocking everything. I don't know what's up with that. I'm going to have to figure out the setting for this to fix it, but I'm on page 5. So I want to show you in code and output in Stata and R what it looks like to fit a linear model for age and then a quadratic model for age. The linear model you already know how to do, but it's a point of comparison. First things first, we got to make a new version of the variable. So I'm centering age at 18. My naming convention for this, by the way, I think I've explained this before, but just in case, I add the constant that I centered at to the end of the new variable name. That way, when I'm reading through my output, I don't have to stop and think about who my 0 is, I just know. So age 18 is the name of the new column that's being created in the Stata code here, as well as the R code here, and the R code also references the particular data set that you're in. A lot of folks will make a new variable and then forget to stick it in the model. They'll stick in the original one instead. So watch out for that as an easy thing that you can accidentally mess up. But if we start with a linear model for age, here's what we get. So let's see, this is Stata output. We have, yep, we'll do Stata output first. So we have model, we have residual. 182 is my residual variance. It started out at 190, it's down to 182. That is a reduction of not that much, 4% from linear age. In terms of the predicted outcomes, my constant, that's my fixed intercept, right? Who's it for? Is my reference in terms of the model. $18-year-olds. I set it up that way. 18-year-olds, according to this linear model, are predicted to make $12,000.3. That's a heck of a lot more than the quadratic model, actually. This one is not a great model. What happens to my income for every year older I get? Slope is 0.2. Not a trick, I swear. Yeah, gestures, I'll take gestures. It should increase by 0.2 per year. Okay, so that means good things for 99-year-olds, right? They're going to be super rich because every year older you are, you just keep getting more and more money. Nope. Exactly. That's it. We get the kids out of the house and then we can start living large again. Yeah, no. Like theoretically, this doesn't make a lot of sense. You would not expect income to keep growing indefinitely. A linear model just is sort of dissatisfying. So I have some examples of making predictions at different ages. In this example, I'm using LinCom. So I am essentially filling in a 1 for beta 0, and I am filling in a 12 for the value of age that I want to multiply the slope coefficient. So in Stata, when you write the names of these variables, what you are actually referring to is their estimated fixed effects. So what it's going to do is this command is going to add 12.3 plus this slope times 12. So it's building predicted values for you. So this is an example with 12. That creates a predicted outcome for a 30-year-old. This is an example with 32 as the value that's being plugged in for age, which creates a predicted income for a 50-year-old. So just a couple different predictions to show what the pattern would look like. In R, we can do the same thing. So mean square error, as it's labeled here, and f of 30. So the model is significant, accounts for 4% of the variance. Here's my 12 and my 0.2. And then to get the same kinds of predictions in R, we use this weird thing. We talked about this on Tuesday. This is like your drive-through menu. I need 1 intercept and 12 linear ages, please. Thank you, drive-through. So this is a dissatisfying model. Even though it's significant, it predicts that income increases indefinitely. So if we fit the quadratic model that we just looked at in the slides, there are multiple ways to specify this in code. This time we'll just look at the R output. In Stata, you can create squared variables by using this thing right here. This is either a pound sign or a hashtag, depending on how old you are. To me, it's a pound sign. So you can create interaction terms on the fly or squared terms this way. You don't have to make them inside your data set as a new column. So note I am keeping the original linear slope of age and adding to it the quadratic one. You can only interpret the squared term slope as quadratic if it's above and beyond linear. Otherwise, it's both of them combined and it doesn't have the right interpretation. In R, I have this thing right here. That's squared in R. So we have age 18, this is a caret, I think, hat, I don't know, caret 2, and then to keep it from actually literally squaring it, we put this capital I out here as a blockade. It's called the inhibitor function. So it makes it so that it doesn't do it literally. The end result of this is squared. So first things that we see, our model looks a lot better in terms of explained variance. It went from, yeah, it was like 4% up to 11% by adding quadratic age. How can I tell if that's significant? Any guesses? Which p-value, though? Good guess, but that's telling me something different. Okay, so this is, we're starting to get into model comparison land here, wading our way in very gently. This p-value right here, that is in bold, is referring to this f. This f is testing linear and quadratic slopes together. So this is testing whether that 11% is significantly greater than 0. Yes, it is. The question that I asked is whether the increase relative to the previous model is greater than 0, and how we might know that. Because that increase is what tells us whether we need the quadratic slope to be added or whether linear is sufficient. So when I phrase it that way, it may get a little bit more intuitive. Maybe not, though. So here's what happens. There's my new quadratic slope. We'll look at the R output here. Zoom in. Its p-value is significant. So that tells us two things simultaneously. It tells us that yes, the quadratic slope is significant. It is highly unlikely to have been found a slope this large if the true slope were 0. And you're like, this is pretty close to 0, but the standard error is pretty small. So this quadratic slope is like 8 standard errors away from the null hypothesis. Definitely into unexpected territory. So yes, it looks like we need the quadratic. Because we need the quadratic, because this made a significant contribution, that automatically means that the change in the R square that new quadratic slope created is also significant. So if I add one new thing to the model and that one new thing has a significant slope, the change in the R-squared that it created is also significant. It's the same idea. Where we're headed next is what to do if you add two things at once. Then there's not a one-to-one correspondence and we have to do something slightly different, but that's in the next unit. So in terms of the pattern, the intercept is now 2.67. It's still the predicted outcome for someone who's 18, but it's predicted from a bendy model instead of a straight line. So it's quite a different prediction, but it has the same interpretation. The linear effective age is 1.22, quite different than before. It has a different interpretation. In these models, this is the linear slope specifically when this term would zero out, which happens at age 18. So the end result is that both the intercept and the linear age slope are specific to age 18. It's where the dot is and the slope of the line at that point. The quadratic then says what happens to the linear slope as age increases. So we start out with a positive slope. The negative quadratic, going to slow it down and eventually tip it over. All right. I was going to say something and I lost it just as well. Oh, I know. Last time I said you only need to remember one thing about quadratics to get them right. You know what the one thing is? Multiply them by 2. That's all you got to remember. Because what ends up happening, why does this keep jumping so much? What ends up happening is the slope at age 18 is 1.22 per year. That slope becomes less positive by twice the quadratic coefficient per year. So it is, the slope at age 19 would be this number times 2 added to it. And each time we would add 2 quadratics to the prediction of the slope. So this is shown in code below. First, state a code to get the predictions. So to get predicted income, I would fill in ages that I want the prediction for. To get the predicted slope, I would start with whatever the age slope is at age 18, and then twice the quadratic slope coefficient times the age value at which I want the new slope. So here's 3 predicted, intercepts, essentially, for ages 30, 50, and 70. And then I also have age slopes. So I have an age slope at age 18 plus 2 times the time value that I want to modify it for. So that's the trick, is this 2 here. And in R, we have the same pattern in terms of these things right here. So you can get predicted age slopes for any age, not just the one that's conditional on the model, in the same way that you can get predicted intercepts at any age. So you don't see this a whole lot in practice, but I wanted to show it to you because these models often get used in longitudinal analysis. So people will put in time and time squared to create a bendy sort of change line. And so you will see that in this context if you do that kind of research. And then I made some pictures. So these are Stata pictures. Kind of looks like the St. Louis Arch to me, I would say. But this is what the model says the predicted income should look like. So down here, we have this positive slope of 1.22. For every additional year, that slope becomes less positive by twice the quadratic. And so then the tip over point is 48 point something. So note that this is centered age on the x-axis. This describes how the linear slope itself changes over age. And it changes by twice the quadratic, a constant amount. So sometimes it's helpful to think about it that way. I also generated predicted values in age to make these plots as well. So this is a much more efficient way to generate predictions than writing one line for each. In this case, what is happening in this case is that I am creating a brand new data set of ages. Okay? And I am creating it with this command that says start at 0, go up to 57 in increments of 1. So that's on the age 18 centered scale. There is a function that works with many, many different R routines called predict. And it wants to know, predict from what? I would like you to predict using this model quad age in this case. Would you like it to predict in the same data, or would you like it to predict on different data? And I'd say, no, I'd like different data. This new list of ages that I just made here called pred quad age, I would like standard errors. Then I put the age variable back in to the prediction that I create, and I make a picture. So I made these pictures in R. And they're really ugly, and I'm sure you can make much prettier pictures if you want to. But that's a whole level of commitment to R that I'm just not going to make. ggplot and other ways there's many, many different ways to plot. I just made a very basic plot right here for this. So in practice, if you want to make predicted values, you don't have to write individual lines of code. You can use routines that sample across them. So the same thing is done in Stata here. Margins is a command that creates predicted outcomes. You know what quietly means? Have you seen that yet in this class? It means don't print it. Which is weird because it should be like blindly or something, right? Because there's no audio file involved in this. Or if you want to turn it back on, it's loudly, I think, right? Isn't there a loudly? Okay. Yeah, but I swear I've seen that somewhere in the documentation, and I had the same question. It's like, is the output going to start yelling at me? Is that what's going to happen? Well, it does. It's just... So in this, I'm doing the same thing in Stata. I'm saying I would like a range of values for centered age that starts at 0 in increments of 1 and goes up to 57, and then take those predicted values and put them in a plot. And you can tell it what dimension you want on your x-axis for models that have lots of variables, and you can save it as an object, and then so those are in your download file to go with this. Okay, I think that's all for that one. In terms of effect size, given that age, linear, and quadratic slopes are working together, I don't think it's helpful to come up with separate effect sizes for each. So the R-square for the model would be the effect size that's most relevant here. How much of the variability in income does age predict? But in order for age to predict it, it takes 2 slopes, not 1. That's the difference. So I've got a little paragraph here as to how I would talk about it, as well as talking about conditional slopes and the point of inflection of the curve as well. Okay. What questions do you have? Yep. I wouldn't say that, but I think her hand went up slightly before yours. Yeah, in increments of 1. Yeah, so this is going to create 58 different predictions. If I wanted it in increments of 5 or something instead to have fewer points to plot, then I could just say like by 5. So you can, that's something you can change. Yep. Question or comments?
To the 12, you said say I take 2 times per 12 like that. Would it be beneficial if you are wanting to help instill the 2 times something that's put 2 times 12 in the parentheses? Would that be okay? Or put 2 times and then your variable and then 12 in the parentheses?
In Stata, I believe you can do that. I think it would, I don't know if they would yell at you or that. I'm not sure if it will let you do it. I haven't actually tried it, but I can play with it and find out. Yes, yeah, that would actually be really helpful if it were broken out that way. I agree. I will look into that. Good idea. Yes. All right. I want to show you one more kind of nonlinear type of trend. Piecewise slopes. This is slide 33, and then we'll look at the model for it. There it was. So in example 2, we had a linear slope of years of education predicting income. That is also as theoretically dissatisfying as having a linear slope of age, because at some point, things stop helping. But education, in terms of years, at least within the US system where these data were collected, is not really just a quantitative variable. There are qualitative distinctions that matter, right? Like if you get a GED or a high school degree, that sets you up for a different type of job than if you don't have that. And the same is true, like incrementally, like yes, more college helps, but it's like if you don't finish the degree, it didn't help. So there's these jumps almost. So if you approach it from that perspective, that you want to think about a relationship both in terms of quantitative terms, but also qualitative differences, then this is an example of one way in which you could do that. This type of pattern here that I'm creating is going to give one slope for the cases that are before 11th grade, another slope from 11th grade to 12th based on this jump that I see here in the means for income, and another slope after 12th grade. So I'm essentially going to divide this predictor into regions and give a different linear slope in each region. This is known as linear splines or piecewise slopes models because you're breaking it into pieces. So something like this would be useful anytime that the numbers have some kind of categorical distinction to them. So where's my psychologist at? We got the pile over here. All right. Give me a measure of depression that you know of. Make one up. I don't even care. BDI, MPS something. What's a bad score on the BDI? Like if you're depressed, where's the cut point where people would say, oh, dude, you need some help? Anyone? No? Do I have to be the psychologist in here? Great, I'm a clinician today.
We'll give you the number 7.
The number 7, yeah, oh, 6, 7. That's when you're really in trouble. Oh, so my cousin, who is a teacher, a high school teacher, put up an alternative explanation on the Facebook, and I was like, oh, she said that it refers to the elements of the periodic table, and it goes with HO. So there's supposed to be a joke with that. I don't know if this is true or not. Yeah, maybe that's what the high schoolers are saying, but not the junior high kids. I don't know, but yeah, so I'm going to give them the Hoffman measure of depression because I'm the psychologist today and I name things after myself. It's fine. And on my scale, clinical depression starts at 6, 7. Right? 6 to 7, okay? So I might want to look at whether depression relates to something, physical activity. How about that? Depressed people don't want to move. I could look at whether the relationship between physical activity and depression is the same in subclinical depression, like 1 to 6, versus clinical depression. Like 1 unit more might have a bigger impact if you're on the high side than if you're on the low side. So if you have hypotheses about things mattering more in certain regions of a variable, you can break the variable into those regions. Where these models are used very frequently is again in longitudinal data. That's my research area, and that's why I'm sticking this stuff in here because I want you to have seen it. In intervention designs. So it's very common to have like a baseline period where you're measuring folks, leave them alone, do something to help them, measure them for a longer time under that new treatment. Maybe you take the treatment away to see if they can maintain whatever you did, right? So time happens in these sections or epochs, people would say. Like I have my baseline era, I have my intervention era, I have my post-intervention era, and I might ask, like, did the intervention work? Well, that's a difference between this era and that one. Did the intervention stay working would be like, is the slope after you took the intervention away the same as it was before? So you're dividing time into sections based on what you did to people during those times. And so these models are very useful in that context as well. So I have one for education. I broke it into 3 pieces so I could show you this. Cool? Okay. Another one that I've seen with these models is something like, let's stick with psychology, how much history of abuse you had as a child. People will give scales where hopefully you see a piling of people at the low end of the scale that said, no, that didn't happen, that didn't happen, that didn't happen, that didn't happen. And then there's some kind of distribution for the people, unfortunately, that have some kind of history of abuse. And there's always this question like, well, do I cut it up and talk about the difference between abusers and not, people who've been abused or not? Or do I keep it continuous and think of it as amount of abuse? And I would say do both. You can do both. So what I would do in that case is I would make one new predictor that's binary, and 0 would be for somebody who zeroed out all the items on the scale, no abuse of any kind, and 1 is something other than that. So that essentially tracks if you have a history of abuse. Then within the people who have a history, they get a second predictor for how bad it was, amount past that point. So then you can see within the group with the history, is more worse in terms of predicting your outcome, but then you can also compare them as a group to people who don't have a history. And so you can have both things happening at the same time. Also something like severity of alcohol use or drug use. It's like you have a pile of people who don't do it, and then you have some degree of variation in those who do. You can capture both at the same time. So I see these models as being useful in a lot of different contexts. The question is how you're going to set up your model to do this. So let me show you the coding scheme that's going to make this magic happen. I'm creating 3 new variables. Those are what's going to go into my analysis. And I base that based on the picture. It looks like there's sort of a flat slope before 11. There's a jump from 11 to 12 in income, and then there's an increase over time after that. Or over years, I should say, not time per se. So my first predictor, I want to capture the changes that happen prior to 11, and then I want it to shut off. So I've decided to make year 11 my reference. So that's the yellows here for the zeros, highlighting that this is going to be my reference group, people who made it to 11th grade. If 11th grade is 0, then 10th grade is -1. We're moving backwards relative to this as an anchor point. So I would write code that essentially subtracts 11 to create all the possibilities of 10, 9, 8, 7, 6, and so forth. I'll show you the code to do this in just a second. Now after 11, this predictor's job is done. So it stays shut off at 0. So if all I had in the model were this predictor, it would have a slope that captures the change in income up to 11 and then shut off. It assumed that there's nothing else past that point. That's because it's like a relay. Predictor 2 is jumping into the game. So I'm handing the baton, and now predictor 2 is carrying it from 11th grade to 12th grade. That's all predictor 2 had to do. Then this predictor picks up the baton and carries it the rest of the way. So relative to this as a starting point, we're 1 more past that at 13. So the first variable gets us up to 11. The second variable gets us from 11 to 12. The third variable then picks up after 12 and gets us the rest of the way. And there's zeros everywhere else where it's supposed to be not relevant. So I've essentially taken my x and cut it into 3 x's. And then each one gets a linear slope. And I'm going to name these predictors less than high school, graduated high school, and over high school. All right, do you want to see how it works? Yeah, you do. You're here. I'm contractually obligated to keep talking. There's that. It could be worse, though. Did I tell you guys about my workshop history? So I used to teach stats workshops in the summer to make money when I was a poor assistant professor with student loans to pay in a house I couldn't afford. Really good gig, by the way, if you can get it. I taught for ICPSR for a number of summers. Went to Boulder for a session, went to Michigan for some. And in those workshops, it's like a 9 to 5 day, 5 days in a row. Exactly, right? Exactly, that face. Oh no. Because these are people, this is pre-COVID when workshops were all in person. These are people who flew, to Michigan or Colorado for the week to, I'm going to learn all of multi-level modeling in 5 days, or I'm going to learn all of structural equation modeling in 5 days. Yeah, it's fine. Yeah, we're like, I have 3 courses on it and they wanted it to happen in a week, but whatever. So I built in an afternoon break and a morning break and a really long lunch break so that it was only maybe 6 hours of actual class. But yeah, by like 1:30 in the afternoon, everyone is checked out. Like they're just full, they're done. But I'm like, we all agreed that we're all going to be here and do this. I'm contractually obligated to talk to like people's heads who are looking down and not looking at me. It's like, okay, this is what we got to do. So the good news is that nowadays, when you feel yourself getting checked out, you can always go back to the recordings from the materials and pick up where you left off. I did not record things back in those days, so they did not want me to because it would cut into their profit margin. Serious. There are a lot of folks who do workshops, and you will not find any of their course materials for their regular courses online because it cuts into their profit margins. In contrast, I believe that I've gotten a number of opportunities because I keep all my stuff online and people can see what they'd be signing up for. Try before you buy, essentially. But let's try this, shall we? So here's the picture I just walked through with you. That will be useful in trying to understand how we're building these new 3 columns. So we'll do state of first and then R per usual. So first step, I'm generating the 3 new columns and initializing them to be empty. That covers my bases in case any education values are missing, so I don't accidentally set them to some kind of default value instead. Again, reading these backwards, if education is less than 12, then do this. So replace the missing values with education minus 11. So that is a function that will fill in this set of values all before 11 without having to do it like one by one, because you can just subtract 11 and have it work that way, just like we do normally. The kicker is that it's only doing it for rows that are under 12. If it is under 12, the other variables are set to 0. Then for the greater than or equal to 12 conditions, after that, I shut off the first one at 0. I turn on the high school graduation binary variable, and then I replace the old one with education minus 12. Minus 12 because 11 to 12 was taken care of by the middle one, so 12 is our reference for what 0 means with respect to the last one. In R, I'm doing the same thing, just with a slightly more convoluted code. I've got my empty columns initialized here. The interior of this is my rows selector. So if education is less than 12, then do this. You want the original variable still selecting just those rows minus 11. That's how that works. The same thing is true on the last one. It's a more convoluted function because we have to have the selector in both of these places for it to work, minus 12. So any questions on how that code works or how to set it up? The whole thing? Yep, okay. So what I'm trying to avoid is having to write a recode statement for every possible value of education, because that's inefficient. So instead, I'm creating functions that are going to fill in these based on rules. So I have 2 conditions that I've separated this variable into. If it's before 12 or greater than or equal to 12. And then I'm writing code that within those conditions specifically. So if I'm creating this column right here, then it would be original education, which is here, minus 11. So I'm only focusing on the rows yellow and above, okay? So this one is created by minus 11. These are all zeros. Then when I get to the switch condition of greater than or equal to 12, meaning I'm covering all of the rows under 11, then this one needs to be original education minus 12 instead, because I want this to indicate the number of years past 12 that you have. Does that help?
Yeah.
Okay, yeah. It's like the logic of it makes sense, but trying to write the code to do it can be tricky. And honestly, whenever I have these kinds of problems, I make a table like this in Excel first, and then I just start writing code that makes it. And then I'll open my data set and make sure that it looks like this. Because sometimes it's difficult to anticipate what would happen, especially with order of operations kinds of stuff. So dividing the rows into sections and then writing custom functions for each of the sections is the idea. Okay. You want to see what happened? Yeah, we do. Education matters. That's your take-home message. Now let's see if we can refine that to be a little more specific. All right. We got, I think I have both, don't I? Yep, I've got output in both. Which one do you want to look through? Stata or R first? R, okay. I know the Stata folks get more of my attention because it's always first. But we've got everything in both packages in its entirety. Here we go. Here is the R output. We'll start there. So in my formula are my 3 new education slopes that I just created, or my new predictors to be given slopes rather, not the original education variable. In this one, I didn't bold things apparently. I was trying to make you guys do it. I'll bold the stuff we got to pay attention to. Okay. What are my numerator degrees of freedom for my F test? 3. Why is it 3? You're right. I'm just asking why. Close. 3 slopes. Yep. Yep. There are 4 fixed effects in total because we have a fixed intercept and 3 predictors that have fixed slopes. Yep, that's why. So if we added a 4th predictor, this would change to 4. How many more slopes do we have room for? Yeah, 730. Yep, so that would otherwise be known as denominator degrees of freedom for your F test. Then we get to F. That is testing whether these 3 slopes significantly predict income working together. So what the model is essentially doing is building a column of y hat based on your education, correlating that column of y hat with the real or income, squaring that, and then that gets me to my R squared that's right here. Question? Technically, yes, but there would be nothing left. I can give you an easy way you could do that. Put in person ID as a predictor. Dead serious. Person ID is a nominal variable, right? It's a number, like person 1, person 2, person 3, but they're not ordered. So if I wanted to do that, if I have 100 people in my study, how many fixed slopes do I need? We just did this. I need 99 because I have an intercept. So I would have slopes that talk about relative to my reference person, how different person 2 is, how different person 3 is, how different person 4 is. That's all the variance in the model. Like you would have an R square of 1 because you've explained all the variance with person ID. That's right. Person 2 is different than person 1, the end. So what am I going to do in my next study? Like, where do I go with that? But you can't because it's gone. Like, you can't put in the 99 slopes for ID and then ask about height or something else mattering because it's saturated. Now, this sounds crazy when I put it this way, right? It does. But this is actually a very common way to deal with what's known as clustered data, meaning when individuals are in naturally occurring groups, such as students who are clustered into classrooms and classrooms that are clustered into schools, patients who are clustered into therapists, I'm back in my psychology hat again, employees who are clustered into supervisors, et cetera, et cetera. If you want to control for that clustering or nesting, you can put in cluster ID as a categorical predictor. That explains all the reasons the cluster differ from each other. Oh, what was up with that? Oh, that's school A. That's the problem right there. It doesn't allow you to test, like, what is it about school A that makes them weird? You just know that they are. So then there is no degrees of freedom left. There's no information left at that point at the cluster level. So you've solved that problem. But yeah, technically you can. Not advised, though. So this tells us 16% of the variation in income is related to education according to this model. So a lot higher than when we had a single linear slope. That is significant. Yay. All right. So then I get to my custom functions. So this function takes the fixed effects table that gets spit out by default, it adds confidence intervals to it, and it formats the p-value a little more nicely. So let's walk through these. Who is my intercept? And don't say 18-year-olds because they're not in my story anymore. 11th graders. And I set it up that way. That's how I know that. Like, that's something you'd have to tell your readers based on your coding scheme. So people who made it to 11th grade but did not graduate high school are predicted to make about $8,500 a year. Now, what happens if you have an education level that is lower? So this slope right here is covering 0 years of education up to 11. See anything sort of surprising? Negative. It's not significant, but it's negative. So this slope of negative 0.26, if the true slope in the population were 0, we would find a result that extreme about 65% of the time, well within expected territory of it being 0. So I wouldn't make too much of it being negative, but it is backwards. And when you look at the picture, you can kind of see that actually. It looks a little slanty down, just a little bit. What happens after 11th grade? Slope coefficient is 4.7. Yeah, it really is that easy. Softball, like, it goes up. It goes up by, so this is the slope, so it's still the change per unit x. But in this case, there's only one change, and it happens between 11 and 12. So this is, you can think of it as the slope, but it's more like a jump. Like, it's just like a shift. And so if you graduate high school, you can make $4.7 thousand more on average. Good reason to do that. Now, what happens after that? Because everyone in this room already graduated high school and probably has some kind of bachelor's degree. Maybe even a master's degree. What happens after that? It goes up, but $2,000 per year of education, then that one is significantly different than 0. Yep. Effect sizes. I added a function that takes that set of results and adds effect sizes to it. So this would be something you could put in a table. So in Cohen's d units, those are standardized mean differences. I would say that the 11 to 12 slope is maybe the only one that would make any sense for. The rest of these are partial r's and a correlation metric instead. And these then you can judge across in terms of which ones are relatively largest. And the largest slope effect size is actually for the last one, right here. Correlation of 0.3. Okay, how are we doing? Now, what if reviewer 3 comes back to you and doesn't like this? Hillary, you have a question or comment? Yeah. Yes, so Cohen's d is used for group differences, and it's a measure of standardized mean difference in standard deviation units. These aren't groups. So this is 0 to 11. This is 12 to 20. and this is 11 to 12. So this is the only one that you can think of as groups because there's only two possible values. And so you can think of this as the standardized mean difference of people who graduated high school versus only made it to 11th grade. That's why. Thank you for the question. Yeah. But where I was going is reviewer 3 is not here for this. Reviewer 3 is like, your model's too complicated, and I think you should just have a linear slope. Fight me. How do we respond? So if a linear slope were sufficient, what would this picture look like? A line, right? So if I take my variable that a line fits the relationship for and I cut it up into 3 pieces, I should have 3 similar lines, right? Meaning that the cutting was unnecessary. Said differently, if a linear slope is sufficient, then there should be no difference across the 3 slopes. They should all be the same slope. So one way to provide evidence that a piecewise model would be needed is to test the difference. That is what these little things are doing in here. So it's in the order in which your output appears. So the first column of this is 0 because that refers to the intercept. And I'm not doing anything with the intercept right now. I'm testing differences between the slope, so the intercept is irrelevant. So for the first comparison, what I want is the difference of the less than high school slope and the graduated high school slope. And I want the less than high school to be the reference for the comparison to talk about how the graduated high school slope differs. So that pattern right here of -1, 1 gets me that. And I don't want to talk about this slope yet, so I'm going to zero that out as well. And then if I want to contrast these two, since they're adjacent as well, that would be -1, 1 in the last spot instead. State of folks, I will show that to you since that is a little bit different. We've got, where's my LinComs? There we go. For instance, there's one right there. You put the -1 and the 1 as multipliers of the variables, and those variables are referring to the fixed slope estimates. Same deal. So our results say, I made 2 functions for this as well. So GLHT summary CI takes the default output, formats it, and adds confidence intervals. GLHT effect sizes then takes that and adds the corresponding R's and D's. So what do we think? The first contrast is significant, the second one is not. So maybe the reviewer has a point. It looks like the difference between the first slope and the second matters, but the difference between the second and the third doesn't. However, if I look at the picture, past 12, does that look like a straight line to you? Yeah, it does. So here's the results walking through the slides. Everything that I just said along with effect sizes. And then, yeah, here's the prediction. You draw a line through it all you want, but it looks kind of bendy. So yeah, you could try a quadratic. It kind of looks like you need extra pieces for degrees out here. So there's the data. You can play with it if you want. I've made that offer to every class and no one's ever taken me up on it. So you can tell me if the piecewise model dividing this into further pieces or quadratic would work a little bit better. But for now, we leave it as linear. So I would say in practice, if I were addressing a reviewer's concern, I would probably not have reported this model in the first place if I could come up with something better. And so then the tests of the slope comparisons would necessarily differ if the model differs. So, but this is the total story right there. Okay. So piecewise models or linear splines. By the way, there are also models where it lets you try to find where to break it up at. So that's a thing too. Essentially where it's called, the terminology that's used is called a knot point. And so empirically, like one of the things that you can estimate is where that breakpoint should be. So folks use that for contexts of, in cognitive aging, for instance, which is the work that I did as a postdoc and junior scholar, there's a thing called terminal decline, where like basically as aging happens, you sort of fall off a cliff. And one of the interests in that field is estimating when it happens, like how many years before death, like you start that. Other ones, like when does puberty happen? Like you can measure like changes in height or something and sort of work backwards to be like, when did this take off or when did this slow down? So those models can be useful as well. There's all kinds of like machine learning things that will break any linear slopes into all kinds of crazy shapes and stuff just to get the best level of prediction. So it's a whole thing, but this is just a tiny little taste of that. All right. Do we have the strength for like one more example? Or should I save that for after I come back? I don't care that I'm contractually obligated. I'm actually asking y'all. Yeah.
But the legal over have to get back to before they mentioned legal freedom.
That seems like a reasonable compromise. Do a little bit now and then re-go over as if I said none of this. Yeah. Because we know from cognition that it's in there, right? We know it's in there, and each time you hear it, it gets a little easier. So having heard it before should benefit even if you're not conscious about it. So here is a predictor of ordinal happiness. I have the black lines here. The bendy ones are the means with an interval around them based on their standard errors, and I drew a straight line through it. So I have unhappy, neither, fairly happy, very happy, or completely happy as my numbers here. First question, are these numbers? Not really. People want to use them that way though. Like I could put in a linear slope for whether happiness predicts income. And since the scale goes from 1 to 5, I could subtract 1 to put it at the minimum and fit a linear slope. So this is what happens when I do that. The predicted income for somebody who rates themselves as unhappy would be right here. That's $15.4 thousand. For every unit of happiness, my income goes up by 0.74. What's a unit of happiness? I don't know. And more problematically, do you think the jump between like unhappy and neither is the same jump as neither to fairly happy, like each of these? So if we think about the piecewise idea in this context, if you can treat an ordinal variable as interval, meaning give it a linear slope in relating to something else, then if I treat it as categorical instead, I should be able to see if the slope from 1 to 2 is the same as the slope from 2 to 3, is the same as the slope from 3 to 4, is the same as the slope from 4 to 5. Like essentially the piecewise model is a way to test empirically whether you can draw one line through an ordinal variable and call it good, or whether that is not going to work. And in this case, it's not going to work because you can see that the scores go up, they go back down, they go up, they go back down. So one line is not going to be a good descriptor for that. So I have an alternative coding scheme that I use in these sorts of situations that I wanted to show you because it's super helpful for ordinal variables. This is a sequential approach. So I have 4 new columns here that I'm using to divide my variable into steps. The lowest answer choice I'm setting as my intercept. Then my first predictor is meant to capture the transition from a score of 1 to 2, and then it shuts off. It doesn't go back to 0, it shuts off. So then this is like a relay race. The next one kicks in and gets me from 2 to 3 and shuts off. And then 3 to 4 and 4 to 5. So each of these contrasts is relative to the score right below it. That way, the slopes that we get out of the model directly capture these adjacent differences, and we can test whether they are different as well. So this is in contrast to this kind of coding scheme that we saw earlier for working group. Okay, and I have the red box here for the difference. The zeros in these off diagonals are replaced by 1s here. So the end result is that in the lower box here, where it goes back to 0, it essentially resets the reference group back to low. Whereas over here, we don't have a reset. So it doesn't go all the way back to low, it goes to where it left off. So then these are just steps. So I think for questions that involve more, like is more happiness better, like being able to phrase it as each step is more useful than comparing back to a value of 1. There's also an article on your reading list that has other ideas for how to represent categorical variables that can be very useful, so I would encourage you to check that out if those are things that you're going to have. But here's the picture that I made. It turns out that money does not relate to happiness. It doesn't. So I have these 4 adjacent slopes. Go up a little, go down a little, go up a little, go down a little. And I also tested the slope differences. Is this slope and this slope the same? Yes. This one and this one the same? Yes. This one and this one the same? Yes. So all in told, yeah, a line probably would have been sufficient. However, the line is flat. There is no relationship. Now up here, here's a result we have not seen yet. I have an F of 1.25 and a p-value of 0.29. So this is telling me that overall, there is no relationship between happiness and income as far as these 4 slopes are creating. The model is not significant. It accounts for less than 1% of the variance. So the 4 slopes do not create a predicted y-hat that is significantly correlated with the real one. Good to know, because it would be sad if money did buy happiness. It does up to a point. I know that. If you don't have what you need to live, you're not very happy. But once you get that under lock, then hopefully things improve. Yes?
Would you suggest
I would. So if like, that actually, the homework that you did last year that I ended up carving out this year to make room for other formative assessments had a problem like that. It was, so mother's education is a good example of a variable, because what it ends up being in data sets often is like less than high school is 1, or high school is 2, college degree is 3, graduate degree is 4, right? Those aren't equal steps in terms of education, and they're, even though they're equal numbers. So I would do something like this to test the difference between them. See if you can draw one line through it all, even though 1 to 4 doesn't really make sense, like empirically it would be supported. So I would do that. Yep. Mm-hmm. Yeah, they're not numbers. People want to make them into numbers, but they're not. It's it can. Indeed. Better late than never, right? Yes. Yes. All right. So then, next week, what's happening? No class, but Michael will be here on Tuesday in the room. Is that right? Hillary will be on Zoom. They'll both be on the Zoom on Thursday because we're getting kicked out of the room. So you can be working on homework, right? That's what's due next. That sounds right, right? You have a homework due? No, I do not have office hours next week. I will be on the road the whole time. Yep. But y'all are. Yep. Okay. So then you can work on your homework and I will let you know when anything else is ready. Cool. Thanks for being here. I will see you in 10 days or so.